notes in that traditional sort of sense. You copy down as much as you want. I'm going to talk, and you guys write down what you think will help you in the future. You like that? Thanks for noticing. Yeah? I saw it online. I was like, yeah, I got to have that. Can't see from there, Mustafa? Mustafa's getting serious. Okay, so let's begin. So we are going to derive, that's really tiny, derive the impulse momentum equation from Newton's second law. You don't need to write that down. I'm going to relate the impulse momentum equation to real life situations. I probably won't show the demonstration today because I want to make sure I get through it all. But remind me to do the blow dart demonstration because it's pretty cool. And we will solve some problems using the impulse momentum equation. Now, why do you think I've got a picture of a golf ball in the golf club there? Well, and I'm going to relate this to a real life situation. So golf is one of those real life situations. So here's the derivation. It's pretty simple. Oh, hang on, not there yet, I guess. So this is kind of a quick review from yesterday. Again, how much you write down is up to you. So consider the following examples. A car and a train are traveling at the same speed. It would require more force to stop the train than the car. How come? Big mass, smaller mass, right? A bullet fired from a gun penetrates a wood block more than a bullet of identical mass that was thrown by hand. So if you throw a bullet at the wall, it's not going to make a hole, is it? How come? Right? Big velocity by hand, small velocity, right? Mass and velocity combine together to provide or to give you that momentum. Just a quick review from yesterday. So these two cases are a result of momentum. Momentum is the product of the mass of a moving body and its velocity. We saw that yesterday. P equals m times v. This you learned back in probably grade 10. A equals delta v over delta t, where delta v is the change in velocity. A brief reminder that v bar is not the same as delta v. Not the same. So if A equals delta V over delta T, what I'm going to do is I'm also going to look at Newton's second law, which is F equals ma. You know, Newton's laws, action, reaction, object in motion stays in motion, all that good stuff, right? So I'm going to take F equals ma, and I'm going to replace this A with that A. And I get F equals m times delta V over delta T. It's average acceleration because it can change. Whatever you think is necessary, Nate. Well, it's going to, in a post-secondary situation, they're not going to say, Nate Urey, write this down. Attention, Nate Urey. They're not. I'm training you for that. I'm going to post this later, so you can get it later if you want. It's up to you. So I got A equals delta V over delta T, F equals m delta V over delta T. Now, most people don't like fractions in their formulas. Okay, so we usually, what we do here is we're going to take both sides and multiply by T on both sides. Okay, and we're going to get F delta T is equal to m delta V. That's the formula derivation. It's one step, a whole lot easier than the other ones. F delta T is equal to m delta V. This is known as the impulse momentum equation. In my vernacular, I call it the fat nav formula. F delta T doesn't stand for anything. The delta kind of looks like an A. Fat equals nav. And every kid that's gone through this school, if you speak to someone that's taken physics like 15 years ago, they'll know, oh yeah, fat nav, yeah, that's what I call it. Okay, so the product of a force and the time interval during which it acts is called the impulse. It's called the impulse momentum equation because the fat part, the F delta T, is called the impulse. It's the product of the force and the time. Impulse, F delta T. Okay? And the letter for impulse, just FYI, is the letter J. J is for impulse, although it's not used that often. F delta T is called the impulse. It can also be referred to as a change in momentum because the second part is M delta V, right? And MV is momentum. So M delta V, change in momentum. Okay, so since the change in momentum depends on the force and the time that the force acts, this has some use in sports, following through, blow darts, what have you, right? How much more have I got here? Do I need to talk about that right now? Yeah, no. Okay, so, for example, when you're hitting a baseball, right? Why do you follow through, Cole? How come? Here's the reason, right? Oh, I got to do this first. I'll play my little video game. Oh, really? Okay, so does the mass of the baseball change whether you follow through or not? Remains the same. If you follow through, which of the two things on the left do you increase? Time. Right? You increase the amount of time that the bat is in contact with the ball. The force remains the same, and because the time part gets bigger and the mass of the baseball remains the same, for it to be equal, the change in velocity must get bigger, which means that it goes farther. That's why you follow through. Okay? And that is true in baseball, it's true in golf, tennis, just about any sport where you're hitting something. To make it go farther, you want to follow through to increase the time. Now, the reverse is true in a car crash. Why do they make that crumple zone at the front? What does it do in the crash? It creates more time, right? Does the velocity of the car change because you've increased time? No. You were doing 100 at the start. You're still doing 100. Does the mass of the car change? No. So this side, no, the mass of the car doesn't change. So the right-hand side stays the same. So when you increase the time to make them equal, what do you do to the force? Make it smaller, which is good. You want the force to be smaller. That's why they build that crumple zone. It's the same principle. It's the same one as they're following through, just in reverse. Okay? If you decide to jump off the roof, should you lock your knees or should you, bend them? How come? Increase your time. As you increase your time, you decrease the force. Okay? When you're playing second base, right? And you're fielding that grounder, what do? You go like this, right? You increase the amount of time you scoop it in. That's why. It's the physics part. Okay. Let's do a couple sample questions. Have I got time? Yeah, I think I do. There are no handouts here, boys. These are just notes. Talking to Frank and Joe Tardy back there. So what force will give a 1 kilogram mass a velocity of 4 meters per second in 3 seconds? Here we are. We're simply applying F delta T is equal to M delta V. Or as I like to say, fat equals math. We are solving for the... Oh, I got to wait for you to write the question now, don't I? Sorry. I'm such a jerk. Pretty straightforward. Like, you guys could probably do this already. It's not that hard. Right? So we're solving for force. The delta T is 3 seconds, so F times 3 is equal to the mass is 1 kilogram. The velocity is 4. So I got F times 3 is equal to 1 times 4. How do you get rid of times by 3? Divide by 3. So 1 times 4, divide by 3, 1.33 newtons. Oh, I should tell you also, I'll let you copy that down. Many of you probably solved it already. The unit for impulse, like if you ever get a question where it asks for impulse, you'd have J equals F times T, and the unit for impulse doesn't have its own name, it's just Newton seconds. Okay, so the unit for impulse is Newton seconds, and it's usually written like that, sometimes without the dot. Yeah, it does, sort of, doesn't it? The unit for impulse is the try it again. J equals F times T. J is impulse, force times time, and the unit is, oh, I did it again. The unit is Newton seconds. What's the unit for momentum? Kilogram meters per second. So that actually means that 1 Newton second is equivalent to 1 kilogram meter per second. They are equivalent. Newton seconds and kilogram meters per second are equivalent. Let's try this one. I'll give you a second to write it down. I apologize for not having these typed out for you. Quickly, let's jump right in. 10 Newton force acts on a 2 kilogram mass for 5 seconds. Find the impulse, delta P, final velocity of the object. So impulse, I guess I could have waited on that Newton second thing until I got to here, right? Impulse is F times time. Quite often, the little triangle part sort of disappears because usually time, the initial time is what? 0, right? So we never have to sort of worry about that subtraction, but for completeness, I'll leave it in there for now. So the impulse is going to be 10 times 5. So we have 50 Newton seconds of impulse. The delta P is the change in momentum, right, which is the m delta v. I got the mass, but I don't have the velocity. But remember, the impulse, the fat equals the mass, right? Right? So your delta p is 50. The impulse is equivalent to the change in momentum. No. So it's going to be 50 is equal to m delta v. The impulse, Nate, force multiplied by the time is equal to the change in momentum. You could even write fat equals mav and do it all in one step if you want. I'm just sort of showing you in the small steps, right? So you've got here 50 is equal to, what was the mass? Was it 2? Okay. So that means that delta V, of course, 50 over 2, 25 meters per second. Oh, I'm sure it was. This is sort of the long way. You can just write fat equals mav and just substitute and go from there. Yeah, absolutely. That's the way I recommend it, actually. You could do that too, yeah. Yeah. I mean, that's what I've done here, right? Yep. These aren't hard. These are really easy. Are they calling you down, Kyla, or are you just guys supposed to go? Okay. I knew he was going to say that. What's your vector, Victor? Okay, last one, I think. Last one. How much time will it take to slow a 5 kilogram body moving at 20 meters per second to 5? The braking force of 10 newtons is applied. Let's do it the Nate way. Can't believe I'm saying that. Okay, so I'll do it quickly because I know you guys got to go. How much time will it take to slow a 5 kilogram body moving at 20 to 5? The braking force, you have 10 newtons applied. So I got 10 is my force. We're solving for time. My mass is 5, and I don't have my delta V. Maybe you want to write delta V equals VF minus VI, but we're all big boys and girls. We can probably just write 5 minus 20 because it's 22.5, so it's going to be minus 15. I'm going to finish this. I don't care what you guys say. Oh, come on, you can solve that. Five times minus 15, 30, 60, 75, right? We'll have to talk about why it's minus. You're right. We'll have to talk about that tomorrow. See you later.